Imagine holding a grain of sand. It seems simple, right? Now imagine that inside this tiny grain, there's an entire universe. This is the world of atoms, the fundamental building blocks of everything we see, feel, and interact with. From the air we breathe to the stars in the night sky, everything is made up of atoms. Understanding these tiny particles is like unlocking the secrets of the cosmos. It's a journey into the very essence of existence. But how did we discover these invisible particles? How did we unravel the mysteries hidden within the atom? It's a thrilling story of scientific curiosity, ingenuity, and the relentless pursuit of knowledge. Let's embark on a journey to the heart of matter, to understand the building blocks of our universe. Our story begins in the late 19th century with a physicist named J.J. Thomson. He was experimenting with cathode rays, beams of electricity passing through a vacuum tube. Thomson discovered that these rays were not made of light, but of tiny negatively charged particles. He called them corpuscles, but we know them today as electrons. This discovery was revolutionary. It showed that atoms, thought to be indivisible, actually contained smaller particles. Then came Ernest Rutherford, a New Zealand-born physicist who conducted an experiment that would change our view of the atom forever. He fired alpha particles, which are positively charged, at a thin gold foil. Expecting the particles to pass straight through, he was astonished to see some deflected at sharp angles. This meant that atoms were not solid spheres, but mostly empty space, with a dense, positively charged nucleus at the center. This is how the proton, the positively charged particle residing in the atom's core, was discovered. While the discovery of the proton was a major breakthrough, it created a new puzzle. Scientists knew that the positive charge of the protons in the nucleus should repel each other, tearing the atom apart. Something was missing, a neutral particle that could provide stability. Enter James Chadwick, a British physicist. In 1932, he performed an experiment where he bombarded beryllium atoms with alpha particles. This resulted in the emission of a new type of radiation that was neither positively nor negatively charged. Chadwick had discovered the neutron, the missing piece of the atomic puzzle. Neutrons reside in the nucleus alongside protons, contributing to the atom's mass, but not its charge. The discovery of the neutron completed our basic picture of the atom, a dense, positively charged nucleus of protons and neutrons, orbited by a cloud of negatively charged electrons. But the story doesn't end there. We needed to understand how these particles interact to form the vast diversity of elements in our universe. While protons and neutrons huddled in the nucleus, electrons were a different story. In the 1920s, physicists like Niels Bohr and Erwin Schrödinger developed a new model of the atom. It wasn't about electrons orbiting the nucleus like planets around a sun. Instead, electrons existed in a cloud of probability with specific energy levels. Imagine a bee buzzing around a flower. You can't pinpoint its exact location, but you know it's within a certain area. That's how electrons behave. They occupy regions called orbitals, each with a specific energy level. The further an orbital is from the nucleus, the higher its energy level. Electrons can jump between these levels by absorbing or releasing energy, which explains phenomena like light and color. These energized electrons, especially the outermost ones, hold the key to understanding how atoms interact and form bonds. Imagine atoms as tiny dancers, each wanting a full dance card. This card is the outermost electron shell. Atoms with full shells, like noble gases, are stable. Most atoms don't have full shells. They gain, lose, or share electrons to achieve stability. Valency is the combining power of an atom. Sodium, Na, loses one electron to become stable. Chlorine, Kil, gains one electron to become stable. This electron transfer forms an ionic bond. This is how table salt, NaCl, is formed. In covalent bonds, atoms share electrons. Two hydrogen atoms share electrons to form H2. Understanding valency helps predict compound formation. Our journey through the atom, from the discovery of its fundamental particles to understanding valency, reveals a profound truth. The universe is built upon elegant simplicity. These tiny particles, governed by fundamental forces, interact in countless ways to create the dazzling diversity of our world. Knowing about atoms is not just for scientists in labs, it's for all of us. It helps us understand how medicines work, how materials are designed, and how energy is generated. From the food we eat to the devices we use, our lives are intertwined with the wonders of the atomic world. So, the next time you look at a grain of sand, remember the universe it holds. It's a universe teeming with wonder, waiting to be explored.